So back in high school, I got really bored in math class. Not that I ignored the teacher, because for one class in particular, pre-calculus, we did review for most of the year. So I had done the homework, I had done the worksheet, I had done the classwork, I had done the homework for the following entire week. And I was bored. So what did I do? I can't go on my phone and play games. People got suspicious when I would just sit there and draw the entire class that I'm not paying attention. I know. I will go and draw something on the calculator. So here's what I decided to do. Here is a radiation symbol. Let's draw it. First thing we need are the ratios. And how do we make this thing? It's split into 6 segments of 60 degrees. These big outer parts and the inner circle. So how in the heck do we draw this? Much less in one function. The first thing is, this is a graphing calculator, not some piece of software. So how do I fill in this? Fill. Well, the first idea would be, okay, maybe I can take a circle. We can graph a circle a number of ways. X squared plus y squared equals 1. We have parametric, where x is equal to sine of t and y is equal to cosine of t. Heck, we can use polar. R is equal to some constant. Let's call it 1, just to be consistent on the radius. That's the word. Don't mind my stupidity. Using this, using the function mode on the calculator, we go across x one time. That's not going to be enough to draw two points. So this is out of the question. We are not using this. And parametric mode, as powerful as it is rather clunky. If I have some function for the amplitude here, I have to write it down twice on a graphing calculator. So I would prefer not to use that. So we're going to be using the polar mode. So polar mode graphs the radius as a function of the angle, theta here. So how do we fill a circle? Keep in mind, we have to somehow filter that to get this. The first idea I had is, well, you can change the step of the graphing calculator, because it doesn't draw a smooth line. It draws lots of little lines. And maybe if you draw them a little bit further, and you're literally just going across the circle at this point. Okay. So that works. It'll fill in the circle, actually relatively efficiently for what the graphing calculator can do. The problem is, it would go right through here. It would go right through, which means we would have to set the amplitude to 0. And it's a big mess. Ideally, I would like to write this function without any, with pure mathematical things, not, oh yeah, go fetch some value from maybe from the clock, and then go do a whole bunch of hashes on that, and there's your random value. No. Alright, well, we can emulate that. We can have the amplitude changing as a sine function. And we can do this as like an irrational multiple of x, or sorry, theta. So that way, it'll go out, and it'll go in, and go out. And the point is, it won't line up, ever, theoretically. Well, because there are 6 parts, we're going to have to split it. Okay, how do we do that? How about a rounding function? Basically, we have from 0 to 1, and we have it go here, and then here. And then our approximation will go here somewhere, and hopefully not ruin things. But for the moment, let's just work with a rounding function. On my calculator, which is a TI-84, it is round function and decimal points. How does this help? It's going around in a circle as a function of theta, which means one full circle is from 0 to 2 pi. And a normal sine function would be something like this. What we want is to somehow split it into 6. Above and below and above and below. See what I mean? So, the way to do that is to multiply it by half. So we multiply the amplitude by 1/2, and then we shift it up, which will now get us either a 0 or a 1. So it would be 0 down here and 1 up here. I split those. 1 up here and 0 down here. Alright. Still not 6. Alright. Just multiply the frequency by 3. 1, 2, 3, approximately. And alright. So I've actually written that out right here. So we have our amplitude, our frequency multiplied by 3. We have our sine function, and I've taken out the 1/2, but it's 1/2 and add 1/2. Because if we add 1, it's up here. You only get 1 or 2 for these little points up here. So if I graph this function, and I zoom in over here, it goes between 1 and 0 repeatedly. 6 times every 2 pi. Now let's go back to our fill. What do I have written down here? Well, very similar. Because sine, the range of sine, back over here, goes from -1 to 1. What we want to do is get this to 0 to 1. So what we do is, for this, we multiply it by 1/2. And then we add 1/2. Very similar. Now I've actually simplified this out. And let's graph this. So, here's our function. It starts here, and it goes between 0 and 1. A rational multiple of this one. So you can see that it never lines up at the same place on this line. That's what we want. Now, why did I have that power there? Well, because this ranges between 0 and 1. If we raise it to a power, that range doesn't change, but the distribution does. And because there's more area toward the outside than the inside of the sine, if we raise it to a power, it actually, let's say 0.5, there's more of it towards 1. Now if I raise this to a very large power, it's almost all 0. But if I raise it to a small power, like 0.2, we get a distribution like this. I'm pulling numbers off the top of my head, but I think it'll work. We have these two amplitudes that we want. This one for the outside, the big part, and this one for here. The way this will work is as it goes around the circle, for this section, the amplitude will only be here. So it'll fill in this entire thing. When it's here, the amplitude is actually here. So it fills in like that. That's why it's negative. So I've just scaled this up to avoid the 1.5. We take these, and we take the function that we want for splitting this, which I actually forgot to write down on the iPad, which is round 1/2 1 plus sine 3 theta plus pi. This is just a phase shift, so it takes the sine wave and shifts it down a little bit. Alright, so we have this. Hold on, I'm going to change a couple things. We're going to call this F for fill, and we're going to call this A, because A. There is nothing more you need to know about A. It is just that. So we have these two ranges that we want to produce using the fill function and A. A is effectively discontinuous. It goes from 0 to 1. And F has ranges from 0 to 1. Okay. How do we combine these? For no particular reason, we're going to say that lines up with this range. Then we can take the range of F, and figure out what we need to do to it in order to get there. So for this, we have a range of 1 and a range of 4. Which means we need to multiply by 4, and then we get 0, 4. We just need to subtract 2. Similarly, multiply by 7 and add 3. Alright, now we worry about A. There. If A is equal to 1, I'm sorry, I'm butchering this. If A is equal to 1, whatever we multiplied by this is equal to 0. And similarly, A is equal to 0. Then this will equal 0. What we're doing is we're just going to take these. 4F minus 2, and 7F plus 3. If A is equal to 1, doesn't really have a difference except for differentiating the two. This is 0, and this is 1. This is all 0. This is 1. This is the only thing in our function. If A is 0, this is all 0. This is 1. This is the only thing. Let's just add them together. And do some algebra. Because this is something that's discontinuous, and I want to approximate. So I only want to write it down one time. A7f plus 3a plus 4f minus 2 minus a4f plus 2a. Did I do that right? Plus 3a plus 4f minus 2 minus 4af plus 2a. I believe so. Let's combine like terms and collect all of our terms with a. Like term and like term. All right, this is just 5. We're going to factor out a here. And combine these because I have okay. 3f plus 5. So this function, we only have to write our approximation of rounding one time. And if I go over to Desmos here and play the animation, when a is equal to 1, it ranges from 3 to 10, as expected. When a is equal to 0, it ranges from -2 to 2. Awesome. So we have our 3 functions right now. We have the range, we have our fill, and we have our split. And just throw these all together. So we take our the splitting function, and we replace that in our range function for a. And then for every f here, we replace it with this. And we shift it by pi. Just a phase shift. It's just a sine wave going from here to here, or one of the other. And we set this as r of theta. So what does that look like? I've got it right here. Let me turn that off. In sections as it jumps back and forth between the two. So here's what it looks like. Let me turn off all the lines. Quite a neat little sequence. And basically, what we do when we grab this equation and we put it in polar coordinates is it just wraps around itself, right around the origin, right here. And this is how much of it is wrapping. So if we have nothing, it doesn't do much. And as soon as we crank up that number, there you go. Can I see the entire equation? And sometimes it just decides to break if you try to put in big numbers. $2,000. Sure, we'll leave it at that. I believe it's starting to do what the calculator does, and it starts taking discrete, visibly discrete steps, and it's jumping across So if we do this on a graphing calculator with a dot mode, so basically it plots little points instead of drawing a line in between each value of the function, it'll eventually fill out. Just leave a really big value and go do something else for a couple minutes. Yeah. I nearly forgot our rounding function. .5 times 1 plus sine 3. Once again, we can do a little power trick, but we want to do that here. Ooh, that's interesting. But not what I'm looking for. This is what I'm looking for. But basically, by doing that, it is getting fairly close to what we want. And my question is, can I just add this? Will it work? So instead of round here, we're going to hide this. That's pretty neat. Let's make it real nice and big and see what it does. I think that's pretty cool. Don't you? Alright. What am I here for again? Yeah. As fascinating as this is, I think it's a failure. Our approximation is not good enough. So it would seem. Am I doing the same thing? 0.04. Let me try 0.04. Actually, I'd say that's pretty damn good. That looks good. To me, at least. You can have your own opinion. Or you could try to approximate the round function with a series of sine waves. And I forgot to address what happens when you unphase shift it. It just rotates. That's literally all it does. 3.1415926535897, I think, maybe. 323. That's enough of pi. That's more than enough. Stop.